Hello, Berkey Academy viewers. This is the first video in a series of 3 videos on intermediate and kind of getting into a little bit of advanced consumer theory here. And I wanted to share with you a worksheet that I made. Now, I've actually already made the second video in the series, but I got such a good response from that I decided to put all of this information on one handout here. And in this first video, I'm going to go through this handout. And of course, you can download this handout, and I encourage you to do that before you watch this video. Go to www.berkeyacademy.com, and on the left side of the screen you will see a link for Files, and go to Files and download this, and I will call this this handout consumertheory.pdf. So I'll call it consumertheory.pdf, so you will be able to find it. And I'm calling this the preliminary version because I've just been working on it, and I might add or fix or update some things here. And if you have any suggestions or additional questions you might think I might be able to pack in here, please let me know. But let's go ahead and get started. In consumer theory, in an economics class, typically you want to start with a utility function, and so I'm going to zoom in to the left side here so that we can see things a little bit more clearly as we talk about it. So usually you will want to start by talking about utility and a utility function, and from that starting point you want to be able to do things like maximize this person's utility and get what we call Marshallian demands. And then after you get the Marshallian demands, sometimes you want to go further and get what we call indirect utility functions. And sometimes also you want to kind of look at the dual problem. The dual problem means instead of maximizing utility, we want to minimize expenditure. And so what this worksheet does is it tries to walk you through all these various relationships. So deriving Hicksian demand functions, expenditure functions, and even on here I go into some things like money metric utility functions. So let me walk you through how this sheet works. And on the sheet I have also an example that I go through. And in the next 2 videos in the series, what I'm going to do is actually show you how to do the examples that you'll see in blue. So here I just list the results, but in the next 2 videos I'll actually walk you through how you find those results using a program called Maple. But I also talk you through the math that you're doing as well. So let's get started here. So under the left side we're focusing on the Marshallian demand function and related sort of functions. So to get a Marshallian demand, you start with a utility function. For example, utility might equal x to the 0.3 times y to the 0.7. That's a Cobb-Douglas type utility function. And you want to maximize that utility subject to some budget constraint. Now, in some classes, you might be given particular prices, like $3 for the price of X and $8 for the price of Y. And you might be given some example budget to solve a particular problem with. So you might be given a budget of $100. Or you can just leave all these things, the price of X, the price of Y, and the budget as variables, and solve for what these functions look like in general. And that's what I've done in this example. But by plugging in, you can get a particular solution. So if you start with a utility function and a budget constraint, now other people might call the budget I for income or M for how much money you have. You use calculus, and in the next video I'll go into the details about how you can do that to solve for the functions that give you the optimal x star. So when you see a star, usually you're talking about a solution for a function that gives me the optimal amount of x that I should purchase, given a certain price of X, price of Y, and budget. And if you're looking at two goods, then you need a optimal solution for how much Y you should buy, Y star, given a price of X, a price of Y, and a budget. For this particular example, if you use this utility function, then the solution you get, the function, is that the optimal amount of X depends on the budget and the price. And so X star would be 0.3 times the amount of money divided by the price. And you see here this solution should make sense in a couple of ways. As the amount of money you have, your budget gets bigger, the numerator gets bigger, and you want to buy more X. But as the price of X gets bigger, since that's in the denominator, you're going to buy less X. Now, one of the curious things about using a Cobb-Douglas utility function like this, u equals x to the 0.3 times y to the 0.7, is that even though in general we expect that the price of y would be in the demand function for x, in a Cobb-Douglas situation, it's not. Only the price of x is. So these two goods are not complements and they're not substitutes. The price of y doesn't really affect the optimal amount of x. And you see the similar sort of situation for the optimal amount of y. The price of x doesn't appear there. That's just something that happens with this particular kind of Cobb-Douglas utility function. So that's normal. Other kinds of utility functions, you'll see the price of y appear in the demand for x. You'll see the price of x appear in the demand function for y. Now, once you get those Marshallian demands, you can either use a Lagrange multiplier method, or you can solve these two equations for two unknowns. The marginal rate of substitution equals the ratio of the prices, and the budget equation. If you solve those two equations and two unknowns, you can get these two optimal amounts for x and y, or equations, depending on how you're doing it. Now, another relationship that sometimes you want to find is called an indirect utility function. And an indirect utility function, what's the difference between that and a direct utility function? Well, I have little notes here in red to help you understand what the function's doing. So again, a Marshallian demand is answering how much x and y you should buy with a given prices and budget, B. An indirect utility function, well, a direct utility function, what we're thinking about is putting x and y into a function to calculate how much utility you're going to get. That's what we call the direct utility function. For example, again, this one, this Cobb-Douglas that we're looking at. An indirect utility function, what you want is a function that uses the prices and the budget to tell us how much utility you're going to get. And this is sort of an indirect route to telling us how much utility you're going to get, because we don't get utility from prices and a budget, we get utility from goods, the x and the y that we're talking about. So an indirect utility function is a function of the price of x, the price of y, and the budget in general. And a lot of times economists will use the letter V to denote an indirect utility function. So U for utility, V for indirect utility. And in this particular example, using this utility function, x to the 0.3, y to the 0.7, you would get this as your indirect utility function. And it's a function of the budget and the two prices. Now, how do you get that function? Well, I'm going to go through that in the next video, but basically on our little map here, you see that in order to get the indirect utility function, you substitute these solutions, x star, like this one, 0.3b over the price of x, and y star, 0.7b over the price of y. Substitute those two solutions into the original utility function. So that's right here. So substitute those in to that function, and then by doing some simplification, I get this function right here. So I just kind of cleaned that up, but basically it's just plugging those into that utility function there, okay? So that's how you get an indirect utility function. Now, suppose you wanted to go backwards. Suppose you were given an indirect utility function and you wanted to get back to those Marshallian demands. How could you do that? Well, take the indirect utility function here. So let me get rid of some of this underlining here. Take this function, and there's an equation called Roy's identity. And Roy's identity says, if you take the derivative of this function, u star, with respect to the price of x, so that's the numerator here, and then you divide it by the derivative of, oops, typo, so this is why this is preliminary, I'll clean this up. Take the derivative of the same function, so this should be the derivative of u with respect to the budget, then you get the demand for x. So you get the Marshalian demand for x. So take the derivative of this function with respect to the price of x, then take the derivative of the same function with respect to the budget, take the ratio of those two derivatives, and that will give you back this Marshalian demand for x. And similarly, if you want to get the demand for the Marshalian demand for y, then you take the derivative of this indirect utility with respect to the price of y, and then you take the ratio of that with the derivative of the utility with respect to the budget. Okay? And that's called Roy's identity, and that will give you this demand back here. So let's look at the other side of the page here real briefly so we can see what's going on. So on the other side, we're starting from the Hicksian demand, sometimes called the compensated demand function. And so what we're trying to solve there is we want to keep someone's utility constant at some level, u bar. And so whenever you want to talk about something being fixed at some level, sometimes people will put a bar on u. So guaranteeing that I get this amount of utility, u bar, maybe it's 100 utils or 10 utils. Sometimes instead of a bar, people will use u naught in order to talk about a fixed level of utility. We want to give somebody that amount of utility in the cheapest way. So we want to minimize the budget, and this is just the budget equation, such that you get that certain amount of utility. So for example, we want to minimize the amount we spend to give you a certain amount of utility, and that amount of utility, again, you could plug in an amount of utility there, like, utility could be 5 or 10 or however much. And when you solve that minimization problem, you get what we call the Hicksian or the compensated demand. So again, you could solve this using calculus, using a Lagrange multiplier method, or you could solve these two equations in two unknowns. So solve the marginal rate of substitution equals the ratio of the prices, and the utility equals some fixed level, u bar or u naught. So after you do the calculus and you get the solution, you get the compensated demands. So usually people will use a different symbol for the compensated demands. Instead of x star and y star, a lot of times people will say x with a C on it for compensated demand for x, compensated demand for y. And these are going to be a function not of, let's go over here and look, not of the price of x, the price of y, and how much money you have, but they're going to be functions of the price of x, the price of y, and how much utility you want this person to get. Sometimes instead of writing them this way, people will still use an x star. So things I have in green are just alternate ways, alternate notation sometimes people will use. And they'll say this is a function h of the price of x, the price of y, and some fixed amount of utility. Okay, so in this particular example, using this Cobb-Douglas utility function we've been looking at, x to the 0.3, y to the 0.7, equals some amount of utility U bar. When you actually solve it, you'll get this Hicksian demand for X and this Hicksian compensated demand for Y. What can you do with the Hicksian demand once you have it? Well, sometimes what people want to do is get something called an expenditure function. How do you do that? Well, first, what is it? An expenditure function asks the question, how much does it cost to get a certain amount of utility the cheapest way, given two prices, price of X and the price of Y? Well, how do you get the expenditure function? It's not very complicated. You take your solutions, X, C, and YC, the compensated demand for X and Y, and you plug it back into this function, this budget line function. So in this particular example, what we would do is we would take this equation, the compensated demand for X, and we'd plug that in for X into this budget line equation. We'd plug this in for Y into that budget line equation. And after doing that and simplifying a little bit, what I ended up with is, so you can kind of see the steps here, and after simplifying it, I ended up with this equation. 10 times that fixed amount of utility times these terms over here involving the price of X and the price of Y. Now again, if any of you, I encourage you, try to replicate this, especially after you watch the next two videos. And if you catch any mistakes in this preliminary version, please let me know. Or if anything's unclear, please let me know. Because I don't want anything that's incorrect to remain out there. Okay, and that's what we call the expenditure function. So you can plug in, say, 10 utils, and I could plug in a price for Y, $5, a price for X, $3. And what this equation will spit out is how many dollars would I need to achieve that amount of utility with those two prices. Okay, that's the expenditure function. Now what if we wanted to work backwards again, right? We've done it forwards. What if we wanted to work backwards? Well, if you have an expenditure function like this, and you want to go backwards to find those compensated demands, so arrow going this way, you can use what's called Shepards Lemma. Now, most of the time we think about Shepards Lemma as being used in producer theory. Because what it's used for in producer theory is to take the derivative of a cost function to find an input demand. But Shepards Lemma is just as useful here because the expenditure function is a cost function, just like a cost function when you're studying production. But instead of producing some amount of output, the output here is utility. So for producing some amount of utility, with the price of input Y and price of input X, we can do the same thing. And what Shepards Lemma does is it says if you take the derivative of the expenditure function here with respect to the price of X, then what you get out is, so take the derivative of that with respect to the price of X, what you will get back is, this demand for X, the compensated demand for X. And if you take the derivative of this function with respect to the price of Y, you will get the compensated demand for Y back out. And that's according to Shepards Lemma. Okay, so we've covered the basics. Let me just mention another couple of things that are on the sheet here that in an intermediate microeconomics class you might not cover. In a graduate level economics class, you probably would talk about these things. You can also use the expenditure function in two additional ways to get what we call a money metric utility function. A money metric utility function answers the question, what's the minimum amount of money I would need to get the same utility as I would get from consuming a particular combination of goods, X naught and Y naught. And so what you do is you plug in an amount of X that you're thinking about consuming, an amount of Y you're thinking about consuming, and the prices of X and Y. And what this will spit out as the output is, okay, we want to get you the same amount of utility as when you're consuming, say, 3 hot dogs and 2 hamburgers. But we're going to tell you how much money you need to do it the cheapest way, right? Because 3 hot dogs and 3 hamburgers might not be what actually maximizes your utility. So we're going to figure out how to get the same amount of utility in the cheapest way. This was called a money metric utility function. And what you would do is plug in the original utility function that u, here, let me use a color that'll be a little easier to see here, u equals x to the 0.3 times y to the 0.7, and plug that into this expenditure function where you see the u bar there. Plug in x to the 0.3 times y to the 0.7 there, and that will give you this money metric utility function. And again, this is after simplifying it, and I think I did that right when I did it by hand, but everybody makes mistakes. If you find a mistake, please let me know. One last fairly interesting, but a little bit less common thing that you can do with these. It's called the indirect money metric utility function. And an indirect money metric utility function is useful when you're comparing 2 situations, say when a price changes. And so what this does is it allows you to put in like some old prices and budget. Say I used to see a price of X of 3, a price of Y of 5, and I used to have $100. But now the price of X and the price of Y have changed. What this indirect money metric utility function does is tell you how much money you need at the new prices to get the same level of utility that you were getting at the old prices and budget. Okay? And in this example, this is what it turns out to be. So what you do is you take the indirect utility function and you substitute it, so this indirect utility function, and substitute that into the expenditure function over here for where you see u. And you can end up with that. And if anybody wants more explanation or an example of that, I can make a video using some examples of the indirect money metric utility function. I'll probably try to cover that in my 3rd video, or maybe I'll make a 4th video. Okay, now something that's a little bit more common to see in, let me get rid of some of these underlines here because it's getting a little crazy. Something that's a little more common question in an intermediate or kind of lower level graduate class is to ask, how can I go between the left side and the right side? So how can I convert a Marshalian into a Hicksian or an expenditure? How can we go between the columns here? And so that's what this information in the middle here is trying to convey. So for example, if you have an indirect, I'm going to have to zoom out here just a bit. Okay, if you have an indirect utility function, suppose you wanted to get an expenditure function from that. How could you do it? Well, it's actually one of the simpler things you can do. If you want to go between an indirect and an expenditure, you just invert the function. So it doesn't matter whether you're going between expenditure and indirect or indirect and expenditure, you just invert it. What do I mean by inverting it? Well, if you take this function, this is utility is a function of budget and the prices, and you solve it for B, solve it for the budget, then what that's going to give you is this expenditure function over here. Okay, so you just solve it for the budget, and what that's going to do is move the utility over to this side as part of the function, and you're solving it for budget. What you'll end up with is this. Budget equals this, and budget is the expenditure, right? Now what if you wanted to go from expenditure to an indirect? You go the opposite direction. So here we have budget equals a function of utility and prices. Solve that function for you, for the utility, and then that will take you over here to where you have the indirect utility function. Easy enough. Okay. Two other possibilities that you might be interested in this discussion. First possibility that I have here in the red. What if I wanted to go from an indirect utility function to a Marshallian demand function? Well, as we talked about, one way to do that would be to use Roy's identity, but there's another kind of trick that you can use to do this, and that's to take the indirect utility function here, plug it in to the Hicksian demand for the utility, and then that will give you, as a result, sorry, I'm saying this backwards here. Plug it in. No, actually, I said it right. I apologize. I'm running out of caffeine here. I need a coffee. Plug it in here for the utility, and that will give you the Marshallian demands back. So plug 0.5423 B over PX, etc. in here for utility. And if you simplify it, and this will take a good deal of simplifying, what you'll end up with is 0.3 V over the price of X. Plug that same thing in here into the Hicksian for U, and it will give you, after a lot of simplification, 0.7 B over the price of Y. Okay? And then the last trick that I'll mention is, what if you wanted to go from an expenditure function to a Hicksian? Well, Shepards Lemma does that. But then another possibility is, if you take this, which is the budget, and you plug it in, so plug that into the Marshallian demand where you see the B for budget, and after doing some simplification, you will end up with these compensated demands once again. Okay? So that's an overview of what's basically, I don't know, a month or so, or at least a good 2 or 3 weeks in an intermediate or advanced undergraduate or say introductory graduate level consumer theory course, all on one page here with kind of the interpretation and the directions all for you. And also here at the bottom I kind of have a legend for what some of the notation means, because that's one of the more confusing things about doing this. So in the next couple of videos I'll actually show you a little bit more of the mechanics of how we take this utility function and get all of these others. I'll be using a program called Maple to do the actual math for us. But I hope you join me for that video. So in the next video we're going to cover all this stuff on the left side from our Marshalian. We're going to cover this stuff on the Hicksian. We won't talk about going between the two columns in that video. And then in the third video, I'll talk about how we go between these two, kind of doing these and doing these inversions. And also I'll talk about these money metric utility functions a little bit in the third video. So as always, if you find any errors or omissions or have any questions about any of this, please leave a comment or question in the comment section below. And as always, good luck in your studies, especially involving microeconomics.